This is video 1I for the Year 12 Mathematical Methods course. In this video, we're going to cover the theory behind the second derivative, under the topic of differential calculus. Specifically, we're going to explore the mathematical notation of the second derivative, how to find the second derivative, and then we're going to cover some example questions. So over the last few videos, we've been looking at a variety of different rules and techniques that we can apply to find the derivative function for a wide range of different types of functions. And all those functions have been covered under standard polynomials, reciprocal functions, trig functions, exponential, radical, or logarithmic functions. And that essentially captures everything that there is to know about finding the first derivative of any of those types of functions, which is really good. And the key thing about that chapter is that the derivative function always tells us the slope of the graph of the function. So for example, in other words, f dash of a is the slope of the graph of y equals f of x when x equals a. This is the key application of derivative functions. So now what we're going to do is we're going to extend this into what's called second derivatives. Now, essentially, you find the second derivative by finding the derivative of the derivative function. So let's write that down. Now, just in terms of maintaining consistency with terminology, we're going to refer to f dash of x or y dash or dy by dx as the first derivative. The reason being is because that's the first time we take the derivative of the original function. Now that we're looking at second derivatives, we use this kind of notation. We can either use f double dash of x, we can have y double dash, or we've got d squared y over dx squared. And this is all notation for the second derivative. Now you may be asking yourself, well, what's the point of finding the second derivative? Well, much like the first derivative tells us about the slope of graphs, the second derivative now tells us something about the convexity or the shape of the graphs. In other words, whether it goes convex up or convex down. However, we'll be looking at this application a bit more in chapter 3. For now, let's have a look at a few different examples about how we can find the second derivative function. So example A, let's say we've got y equals 5x squared, take 7x plus 2. So in order to find the second derivative, we first of all need to find the first derivative. So y dash will be equal to 10x minus 7 plus 0. However, we can just write this as 10x minus 7. So then the second derivative, y double dash, is the derivative of this function here. The derivative of 10x is just 10, and the derivative of minus 7 is 0. So we can just leave it as y double dash is equal to 10. Let's have a look at another one. Example B, y equals negative 1 over root x plus 3x to the power of 3. So much like any other question that involves radicals, the first thing you're going to do is write this in terms of x to the power of something. So in other words, y is equal to negative x to the power of minus a half plus 3x cubed. So now the first derivative, y dash, will be negative, then negative a half x to the power of minus 3 over 2 plus 3 lots of 3 x to the power of 2. Now, just to make this a little bit easier to work with, I am going to simplify these terms a little bit, only because we're now going to have to use this to figure out the second derivative. So then minus a half will turn to positive a half, x to the power of minus 3 over 2. Then 3 by 3 is 9, so we've got 9x squared. So then the second derivative of this, y double dash, we're going to have a half multiplied by minus 3 over 2, x to the power of minus 5 over 2. Then we're going to have 9 multiplied by 2 then x to the power of 1, which we can just write as x. And again, because these ones here are reasonably easy to simplify, let's just go about doing that. A half multiplied by minus 3 over 2 will be minus 3 over 4. X to the power of minus 5 over 2. Then 9 by 2 is 18, so we've got plus 18x. The last example we're going to look at is now going to incorporate the chain rule and the product rule. So this one's quite a good one to keep in mind. We've got y equals x squared plus 1 to the power of 3. Now, if you really wanted to, you could technically expand and simplify 3 of these brackets. However, as we've discussed before, we do have the chain rule for a reason. It makes finding these derivatives much easier to work with. So let's just go with that. So using the chain rule, we've got y dash is equal to 3, x squared plus 1, then we take 1 from a power, so that'll be 2. Then we need to multiply by the derivative of this inside function. The derivative of x squared plus 1 is just 2x, so I can write that like that. Again, because we will be using this function to find the second derivative, let's simplify this a little bit. So we've got 3 by 2x, which will be 6x, and then we've got x squared plus 1 to the power of 2. So now if we want to find the second derivative, we're going to have to take the derivative of this function here. So we're now going to have to use the product rule. So we've got u is equal to 6x, and then v is the x squared plus 1 to the power of 2. So then u dash is equal to 6, and v dash, once again using the chain rule, is going to be 2 multiplied by x squared plus 1. Reduce 1 from a power gives us 1, so I'm not going to bother writing it. Then multiplied by the derivative of the inside, which is 2x. For simplicity, I am going to simplify this one here. So that'll be 4x, then x squared plus 1. So now using the product rule, y double dash is going to be equal to these two multiplied together. So that'll be 6, then x squared plus 1 squared, plus these two multiplied together, which is 6x, then 4x, and then x squared plus 1. Now, in order to simplify this one, you would have to go through some expansion and simplification, so we're not going to worry about this one here. If you did ever get asked to find the second derivative of this type of question, you would most likely just need to leave it in this kind of format here. However, like I mentioned before, all the steps leading up to the second derivative should be as simple as possible, because if you don't simplify any parts beforehand, it's just going to make the subsequent steps significantly harder to work with. So it's just better if you make those early simplifications to make the final step a bit easier. So that's those examples there of finding the second derivative. Again, realistically, it's just going to be doubling down on the rules that we've already been accustomed to over the last couple of videos, so hopefully it shouldn't be too challenging at this point in time. The other thing which I'm going to be mindful of is that there will be some questions based around finding the second derivative that can either be done a really easy way or a really difficult way. Typically, these come in the form of fractions, and understanding how to simplify fractions before you even find the derivatives will be a very pivotal step. And those are the types of questions that I'm going to be covering in my application video, so please keep that in mind if you do need that extra bit of revision and practice. Alrighty, let's wrap up. So in this video, we were introduced to the second derivative. We discussed how this can be notated as either f double dash of x, y double dash, or d squared of y divided by dx squared, depending on the situation, and how we can find the second derivative by calculating the derivative of the first derivative function. Finally, we found the second derivative of several functions. And that's it for now. See you in the next video.